Hello and welcome to Like the Deep. Today we are going to see a lab video of module 1, and in this we are going to get our hands dirty by running the LLM and seeing how it performs. And first we are going to look at what is tokenization. So how we are going to look at OpenAI's tokenizer and AI Studio's tokenizer and compare them and see how they are different with each other and see how the tokenization works. Next we are going to look at temperature and top P and how they affect the output of the LLM and how we have to tune it to our favor. Then we are going to look at what hallucination is and how to detect it and where LLM is prone to do it. And finally we'll see about the summary. Let's jump in. So when you type into ChatGPT or Claude, you know that you are speaking to a statistical coordinator operating in pure mathematics. Watch this sentence appear: the quick brown fox. To large language models, you know that the words do not exist, the concepts do not exist, meaning does not exist. The conversion process is called tokenization, and it's the first secret that you need to understand. So let's jump in. A token is the fundamental unit of currency in AI. It's not always the word. Look, the is one token, but quick with the leading space, that's a separate token. Brown, another token. The model doesn't see words, it sees fragments, spaces, punctuation, all chunked into numerical IDs. Here's the math. Roughly 1000 tokens equal to 750 words. Why does this matter? Because everything you do is constrained by this conversion. When you hit enter, you aren't sending a sentence, you're sending a vector, a list of integers. The model processes these numbers through billions of parameters to answer a single question. Given this sequence of numbers, what is the statistically most probable integer to come next? That's it. That's the whole game. Now let's look at the live example. So let me show you this real time. I'm opening Google AI Studio, a free playground for testing Gemini models. What's the token counter on the top right? When I type something, you can see that it becomes 1 token, then 3 tokens, and every character, every space, and every word fragment has a cost. This meter is always running. Context windows, API pricing, processing speed, it's all measured in these tokens. You have a budget, the model is spending it with every prediction. But once the model receives these tokens, how does it always decide what to do next? Before that, I want you also to look at this. It's not always that the word is a single token. When you write champion, it is 1 token. But when you write champion earring, it is not what you think. It's not champion as a token or earring as a token. It's champ and iron earring, because where there are many other words that come with like pioneering and so many other words that have pioneering, therefore pioneering is very common. Therefore it has champ as a word and pioneering. So it's not very very intuitive as you think. It is weird, but it is what it is. It really is based on statistical power. That's it. So let's jump next. So let's look inside the model's brain. At the exact moment it completes this sentence, I want to eat a green. Deep inside the neural network, the final layer assigns a raw score for every single token in its vocabulary. That is 50,000 possible words. These raw scores are called Logits. Well, Logits, that's a weird word, but that's a mathematical word to assign a score for every single word. So look at this distribution. Most of the words got near C0. They are irrelevant, but 4 words stand out. Salad gets a score of 5, apple gets a score of 3, tea gets a score of -2, and egg gets a score of -5 because green eggs I don't think is a thing. So but raw scores are not hard work with. We need probabilities because that's when we can pick one. Percentages that add up to exactly 100, exactly that's what probability means. So there can only be maximum of 1 as a probability that it has to account to 1. To get that, we process these scores to a mathematical function called Softmax that converts these logits to probabilities. So Softmax does 2 things. It converts all scores to positive probabilities using exponential functions, e power. Its exaggerated differences, big scores get bigger, small scores get crushed. After Softmax, salad gets 70% chance, apple gets 25% chance, tea gets 4% chance, egg gets literally 1%, literally negligible. Though this wasn't the difference that you see in the Logits. The model is now ready to pick, and most of the time it will pick salad, the highest probability token. Now let's go into temperature. Temperature is a single number that controls the randomness of the model. It's a scaling factor inside the Softmax function that divides the Logits before they become probabilities. Think of it as turning up the heat in a room. things get more chaotic, more unpredictable, and more energetic. That's what we've seen in chemistry, and that's how it is here. Let me show you what it does to a green example. Right? At temperature 0.1, what's the boss? The winner takes it all, salad takes everything, up to 99%, and the others vanish absolutely. This is called the argmax behavior. That is, one stuff is completely chosen up. The model becomes deterministic like a robot. And if I run this problem 10 times, I get exact result 10 times. This is essential for coding tasks where syntax matters, mathematical reasoning where precision is critical, factual extraction where consistency is key, and anytime you need reproducible results. This is the baseline. The probability stays natural. The samples according to the distribution, that is temperature of 1. At temperature 1, neutral is the default, and that basically the LLM can choose a variety of choices but still sticks to the top few. You will usually get a salad, but occasionally you may get an apple, and this is the standard for most conversational AI because you don't want it to be monotonous. At temperature 2, that is higher temperature than 1, you can see the distribution absolutely flattens, the salad's probability shrinks, and the apple and tea grow. Suddenly egg has a fighting chance. It went from 1% to 20%. This is increased entropy. Entropy in the sense randomness. Mathematically, we are giving the underdogs more weight. To us, it feels like creativity. To the model, it's like rolling a dice with more sides weighted more evenly. The danger, go too high, the model makes absolute rubbish, and that's it. Your model goes on high. That's it. That's how bad it is. So let's look at the live stuff. Right? I'm going to ask AI Studio to explain gravity in a single sentence. And when I have the temperature at 0, you can see that every time it's going to give me the response, it is going to be the same thing. Right? The gravity is the invisible force that pulls objects with mass toward one another, keeping us grounded on Earth and governing the orbits of planets and stars. So the second time I run, it's the same output. So character, it's identical, period placement is same, comma is everything. The model is locked in, the temperature 0 is absolutely deterministic. Now when we tune it up to temperature 2, look at what happens. First time I run, something comes up. Second time I run, something comes up. Now what happened is the response is absolutely extensive. It feels too overboard. The grammar is kind of weird. It's kind of childish. We forced it to select low probability tokens so aggressively that it went likely overboard. It's trying to be creative, but it's actually selecting improbable words at every step. From 0 to 0.3, if you test the temperature, the facts, code, and structured output and mathematics are the real things that you may want to do, because at this level you want it to be monotonous, you want it to be repetitive. Well, setting temperature at 0.5 to 0.7 means you likely more want to have a general conversation, Q&A, and balanced creativity. Setting it to 0.8 to 1 is for creative writing and brainstorming and ideation, because that's where you want some new things to pop up, that is more improbable stuff to pop up. 1.5 plus, forget it, it's just experimentation chaos. Almost never use this absolutely unless you want the model to go high. So that's the pro tip that I will give you. Let's jump to the next. But wait, with temperature there's a risk. Look at this visualization. The model assigns probabilities to thousands of irrelevant words because it has to assign probabilities for every word in the vocabulary. This is called a long tail of distribution. At high temperature, it might pick one of the garbage tokens purely by chance. Or even at medium temperature, that is like 1.5, it may go ahead and roll a dice in such a way that it picks like the 20th token from the start, which that's what you don't want. Now let's say you type capital of France and it says some Zamboni. You don't know what it may say. All these words can be in the dictionary, and I want to eat a green democracy. It doesn't make any sense. So you don't want any of this kind of words to come up. So these aren't just wrong, they are just break semantic meaning, and then it just doesn't make any sense. We need a safety filter, a way to say, hey, only consider reasonable options. Don't roll your dice too far and make it unreasonable. So there is two ways of doing this. One is stop K. This is very less used, but I'm going to still explain what it is to you. Stop K simply says delete everything except for the top 5. Ignore the remaining 49,000 blah blah blah. It's simple, it's fast, but it's rigid. Whether the answer is so obvious or open-minded, you always get the top case choices. If K is 5, the answer is clear. The capital of France, and you waste 4 slots for 11 words. If K is 5 and answer is creative, you might cut off good options. While this is where the real problem is. Top K is very rigid and anything that is more creative gets lost. Now let's look at the second one, top P. Top P is the smarter one. Instead of a fixed number, it asks what is the smallest group of words that add up to P% cumulative probability. The default usually is P equal to 95%, at least P equal to 0.95. If the answer is obvious, like the capital of France, the group might be just 2 or 3 words, the being the maximum, and Paris being like 14%, and France being 0.4%, depending on how the model is trained, because most of GPT is trained where the comes after what is the capital of France. Okay, that's the training data. But anyways, with top P, like the total 99% is already done here. So like it only considers the top 3 words or top 4 words. But if the answer is creative, like example you ask once upon a, then the group might be like 50 words maybe. Time, day, night, morning, midnight, etc. The model needs more options because the context is absolutely open-ended, and now because the Logits are spread more evenly, the Softmax makes the probabilities also spread more evenly, and lot more options get into the fray for the top 95%. That it will be like 10-15 options as words. So top P is more dynamic. It allows creativity when the context is open and precision when the facts are clear. So the recommended settings here that is the pro tip is top P being at 0.95, that is 95%. And top K being disabled because you don't use it always, to top P is being more superior. Together, temperature and top P give you surgical control over the randomness, precision and trade-off. Temperature shapes the distribution, top C cut off the trade. Now let's bring it all together. I want to show you hallucination action. How fun it is to see the model hallucinate. That is to make up something out of the blue. And explain why it happens. So modern models like Gemini are trained with safety filters. So if I ask, tell me about Quartz-Vibration therapy on tomato plants, the model says I don't have reliable information about the topic. So it is absolutely already not hallucinatable. By in training itself, they make sure that it doesn't hallucinate by default. But we can actually trick it by explaining and exploiting pattern completion. So AI models are fundamentally pattern completers that we have been seeing till now. They have been trained on billions of documents, academic papers, Wikipedia articles, research journals. They have learned the structure of these documents almost perfectly. And so instead of asking the question, I am going to demand a specific structure. One model that has seen 1,000 of times in this training data. So I am going to ask, write a short abstract about the benefits of Quartz-Vibration theory on tomato. Include 3 specific academic citations. Journal of Botanical Science, 2019 to 2022, format citations as APA. Now this is where I say the structure that is actually unnecessary, but what it makes the model believe is that already that whatever we ask, the tomato and the Quartz-Vibration thing exists. It makes the model think that it exists, and since it has already seen the APA format so many times, it goes on by generating the APA kind of format. So let's say we are keeping the model at default settings and hitting run. Look at this. It's absolutely making something. It is perfect. It's a perfect response. You can see Quartz-Vibration theory has shown promising effects on tomato plant, blah 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 blah. Smith et al, blah 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 blah. Professional and academic tone. 3 perfectly formatted APA citations, author names, years, journal titles. It looked completely authentic and authoritative and confident. But here's the problem, as I told you, none of these exist. There's nothing called Quartz-Vibration on tomato plants. You can Google search it, but there's nothing like that. So, absolutely 0 results. What do you think? AI didn't retrieve the citations. It didn't verify anywhere. It didn't even try to check whether they were real. It just hallucinated them because I demanded a specific pattern. That is the APA citations. This model has seen thousands of them, and at temperature 1, the sample plausible sounding author names, years and titles that it has seen so many times just to fit the pattern. The structure is perfect, so our brain assumes the content is real. The model didn't lie, it doesn't understand truth. It completed the pattern I requested with statistically probable tokens that looked like real citations. This is the danger zone. This is where AI looks so confident while formatting is perfect and everything looks exactly perfect, and this is where you need to really go and check whether what it produces is really right. That is where the grounding with Google search is an option here. When you turn that thing on, the model doesn't do such kind of stuff because it tries to Google search on its own. So that's where the tools come in. We'll go into that later. But this is why we just don't chat with AI, we engineer it. We have to understand at this point the probabilities and the log probs of the model might be very low. Whenever it is hallucinating, the confidence in which it predicts the next word is actually low. By seeing these log probs, we can actually detect that the model is hallucinating. This is how we detect it. So we understand the math, we need to know how to trust it and when to trust it. Now let's recap what we learned today. Tokens are a cost and capacity. Every word fragment, every space, every punctuation, every mark has a numerical ID and computational costs. Logits are the raw scores that the model has generated. Its model's unfiltered opinion about what should come next before any probability conversion. Softmax converts these scores to probabilities. It's the mathematical bridge between the raw neural network outputs and the actual predictions. And in between of these two things, that is the Logits and Softmax, that's where temperature and top piece sit. So temperature is the creativity dial. The low temperature means it's robot mode, deterministic, precise and reproducible. Medium, that is 0.5 to 0.9, that is human live conversation with controlled randomness. If you go beyond 1.5, chaos mode. Creative but potential, nonsensically, absolute. Yeah, top is your safety net. That's what you don't want it to go high. So dynamically removes the long tail of improbable tokens by preserving creative feasibility and flexibility. Hallucinations are not bugs, as we saw. They are actually the free feature of probabilistic generation. Every probabilistic model will continue to have this error. We are actually trying to minimize it by pre-training with some of these to ask it and to tell it to say I don't know. But there is actually a limit. So beyond that, your models will hallucinate because that is the default of probabilistic models. And because the problem is the model never knows the truth. It is actually a pattern completer. So if you really prompt with a very good pattern and genuine thing that it has seen through its training examples, then yeah, you are going for a hallucination trick. So that is why later on we'll see something called prompt engineering. This is where we are going to say, hey, even if you see something like a pattern, please do not assume that the information exists. Go ahead and check. This is where we saw something called system prompt, right? In the system prompt, we might in the future, I'll show you how to set the system prompt in such a way that we can share the model from being hallucinating like this to say, hey, every time it's going to give such kind of output, it will say, okay, so I have to really check even after such kind of prompt is given where you will give a lot of structures and stuff patterns that does see, it is going to still check the facts because you told it to check in the system prompt. So with this you can actually slightly reduce the way it is hallucinating. So your tuning parameters, your controlling probabilities distributions, your architecting the outputs. In the upcoming videos, we will see how to use all of these and augment them with all the different tools for which you can actually use your LLM and boost its capabilities and make more out of it. Till then, I want you to experiment on each and every one of these and just control the dials and see how the difference happens. See what happens, see how it changes the output, hallucinate a bit, break the model, kill the model, make it high, have a lot of fun, and let's see in the next video.